Welcome to today's lecture from Paolo, and the guest of today is Paolo Botticini. Paolo Botticini is a PhD student in the Department of Mechanical and Industrial Engineering at the University of Brescia in Italy. His research integrates analytical tools such as perturbation theory and multiscale analysis to explore multi-phase transport phenomena, including field dynamics, bubble motion, and heat or mass transfer. He will spend the next semester of his final year as a visiting student at Paolo in Rome. But today, he will present the work he developed during his master thesis at the École des Mines in Saint-Étienne. So, please, Paolo, thanks for offering your lecture today. The floor is yours.
Thank you very much, and thank you for this opportunity. Today, I will present our recent work about the impact of compressibility on the descent of thin liquid layer on a solid substrate. This work is a result of a cooperation between the University of Brescia and the École des Mines of Saint-Étienne. And the entire project lasted 3 years. And this is the output of my master thesis. And generally speaking, the project focused on the multiscale analysis of multi-phase channel flows. And I will start with some motivation and an example of the topic. So the motion of liquid films driven by gravity is a subject that has been studied a lot, and has a lot of applications such as absorption columns, heat exchanger, condensers, and so on. And the example I will start with is about carbon capture and storage, because typically the problem of thin liquid film falling down a plate is modeled assuming that the flow is perfectly incompressible. But there are domains of science and engineering in which this hypothesis may constitute an oversimplification and possible may lead to errors. The example I've chosen is about carbon capture storage, because typically in carbon dioxide transport, carbon dioxide is transported in pipes in its supercritical phase, because this makes the transport more efficient. Here you see the phase diagram, and you see that in the supercritical phase, the fluid behaves like a gas in terms of viscosity, and this is the reason why the transport is more efficient. But it has a liquid, not perfectly a compressibility of a liquid, but it has some features that are shared between the gas and the liquid states. So it is important in this case to address how compressibility may affect the flow stability in terms of formation of superficial instabilities along the film. This is important, for instance, to keep under control the development of the superficial corrugations of the film. So here is a sketch of the problem we studied. You see there is an inclined plate that forms an angle beta with respect to the horizontal, and you have a liquid film that in the let me say waveless configuration is the one indicated with the dashed line, and the variables here are indicated with the subscript n, which stands for Nusselt state, because this problem, the one with the waveless configuration, has been studied by Nusselt in 1916. But during the 60s, a lot of attention grew with respect to the formation of these superficial instabilities. And in particular, you have that H here is the dynamic thickness of the film, which is a function of the spatial variable and also of time. The liquid has a viscosity equal to mu0, and there is a surface tension equal to gamma 0. The flow is driven by gravity, and there is an interfacial pressure because we assume that the liquid is sheared by a by a gas. And so we define at the base state the condition of a waveless film, where the thickness is equal to hn and the mean velocity is equal to un. And the novelty of this study is that in this case, we assume that the liquid can have a variable density, rho, which is a function of both the space variables and also of time. So the aim of this study is to investigate how density variation enter the paradigm of Kapitza instability, which are the formation of this corrugation along the surface. And we follow an approach which is typical of perturbation problems. So we define a small scale parameter, epsilon, which in this case is given as an aspect ratio, and in particular is the ratio between the thickness of the film and a characteristic length along the direction of the flow. And in this case, we assume that this scale is given by the wavelength of the corrugation. In this way, we are able to simplify the physics of the problem. We can achieve a simplified description because we will express the motion of the film in terms of integral variables. And in particular, we achieve a reduced order model, which are called shallow water equations, which are in the basic formulation are two integral equations in which the variables are the thickness itself of the film, but also the flow rate, Q. The novelty in this case, given by compressibility, is that these two equations are not sufficient to describe the whole physics of the problem, because we need an additional equation, which is the equation of state, and we will see in a few slides how we model this. So the starting point are the compressible formulation of a Navier-Stokes equation. Here we already made them dimensionless. So you see the continuity equation and the conservation of momentum along the x and y direction. And one of the first feature of perturbation problem is that once you have chosen properly the scales, you can immediately recognize the order of magnitude of each term that appears in the equation. For instance, here you have highlighted in green the leading order terms, the one of order 0, while you have in blue the terms of order epsilon, and in red the terms of order epsilon square. So you immediately recognize a hierarchy of in the terms. We assume that the Reynolds number and the Food number, which are the dimensionless governing group that emerge from the non-dimensionalization, are of order 1, while the problem is dominated by the effect of well, in addition to the Food number and the Reynolds number, we have also, thanks to the boundary condition, the effect of the Weber number, which is linked to the effect of the surface tension of the interface. These equations are also coupled with the proper boundary conditions, such as the no slip at the wall, and we assume that the gas which is around the film has an effect just in terms of interfacial pressure, the normal component, but not on the shear component. So how to derive the boundary layer equation? First of all, we have to replace the partial derivative of the pressure with respect to x in the equation for the conservation of the x component of the momentum. And to do so, we have to obtain the pressure profile from the third equation, which is the conservation of momentum along the y direction. This can be done because you see that in the second equation, the gradient of the pressure has in front an epsilon. So it is sufficient to, if you want to achieve a consistency of the order epsilon square, you simply need to approximate the third equation to the order epsilon. So basically, you do not need to take into consideration the terms of order epsilon square. And in this way, we obtain an equation that we can solve in P. And the second step is to integrate along the depth, along the film thickness, these two equations. So to obtain the shallow water equations that are formulated in terms of H and Q, which is the volumetric discharge. As I mentioned before, in this case, we need an additional equation of state. And to simplify the discussion, we have chosen a barotropic formulation. So in this case, density is just a function of the pressure, and it's given as a summation of the one, which denotes the base state, plus a term which depends on the Mach number, which is the ratio of the characteristic convective scale of velocity of the film divided by the velocity of the speed. In this way, we can capture the effect of compressibility via the variation of pressure and the Mach number that indicates the competition between the convective phenomena and acoustic phenomena. So we have the epsilon momentum equation that can be solved to give the pressure distribution, and highlighted in red the novel contribution due to the compressibility. To solve this ordinary differential equation, which is inhomogeneous, we can write the solution as the superimposition of the solution to the homogeneous problem plus the solution to the inhomogeneous part of the problem. And we follow an approach which is the classical approach used to solve this differential equation that sometimes is termed the Duhamel principle. And at the end, we arrive at the pressure profile. So we can compute its derivative and replace into the X momentum equation. We can also substitute the pressure profile directly in the equation of state. And in this way, we obtain how the density variations enter the problem. To do so, we express the Mach number also in terms of the shallowness parameter, because in this way we are able to identify different regimes. For instance, here you see that if alpha is equal or higher than 3 divided by 2, the problem reduces to its incompressible formulation because the density in dimensionless term is equal to 1. Whereas in this work, we studied the problem where alpha is equal to 1, which is the lowest compressible scenario that is allowed by this theory. And you see that if we linearize the density around the base state, the solution, which was formulated in terms of an exponential function, can be approximated as a linear term that depends on the difference between the thickness of the film and the local coordinate along y. whereas we do not study the scenario with alpha equal to 1/2 because in this case we cannot achieve a consistent formulation for the problem because the equation I showed you in this slide has to be accurate up to the order epsilon square. So we restrict our attention to the case alpha equal to 1. And the final step to achieve the model is, as I mentioned before, to replace the partial derivative of the pressure profile. And in this way, we obtain the compressible formulation of the continuity equation and the compressible formulation of the X momentum equation, which inside has also the contribution due to the conservation of momentum along the thickness of the film. The final step is to integrate these equations along the thickness. But here there is a problem because some terms cannot be integrated. In fact, we do not know the explicit analytical expression, so we cannot perform directly the integration. So we adopt a procedure which is basically an asymptotic expansion of each variable. In this case, the variable are the two components of the velocity, u and v. And moreover, we have the pressure and the density. We can expand each of these variables as a power series, and we can replace this series in order to have a simplified problem where you have basically a cascade of equations, each one at a different order, so you can solve them separately. And once you perform this integration, you achieve the shallow water equation, in this case, the compressible formulation. You see, for instance, that the continuity equation reduces to the so-called Saint-Venant equation when the Mach number tends to 0. But since we are addressing a weakly compressible scenario, we have an additional term highlighted in red in the continuity equation. And also in the equation for the momentum conservation, we have another additional term. The second part of the study as object the temporal linear stability analysis of this problem. So we assume that the variables h and q can be perturbed around a base state, which is the state denoted by the one studied by Nusselt, so the one with a thickness of unitary thickness, whereas we will see a novel expression for the discharge because the fact that there is also the compressibility modifies the flow rate of the film. And the first step is to write the model we derived in this conservational form. So you have a flux term and a source term, and you impose that you can perturb the variables with normal mode waves. So basically a sinusoidal perturbation that moves with a wave number equal to k and with a celerity, which is a complex number equal to c. The real part of the celerity tells you which is the speed of the propagation, whereas the complex part, the imaginary part, tells you how this perturbation tends to grow or to decay in time. And if you replace the perturbed variables into the model, you obtain the dispersion relation, which is obtained by imposing that the system has to admit non-trivial solutions. You find this quadratic equation in C. And once you have this equation, we can check if the perturbation we impose is stable or unstable by studying its growth rate. In particular, if the imaginary part C is positive, you have that the imposed perturbation tends to grow with respect to time. So it's an unstable mode, whereas it is stable otherwise. And to validate the model, we can make a comparison between our dispersion relation and the coefficients that are recovered in the classical or Sommerfeld theory, which was developed in the incompressible formulation. So we can check if the limit, as the Mach number tends to zero, makes these coefficients, this set of coefficients, to be the same. Here I show you some results of our study. In this plot, we have the growth rate of the perturbation with respect to against the wave number for different values of the Mach number. The darkest curve is the one in the incompressible formulation. And so it's a case of marginal stability because the entire curve is below in the negative part of the axis, which indicates stable perturbation. But as you increase the Mach number, you have that this curve tends to shift towards the right, and in particular also the intersection point between these curves and the horizontal axis tends to move in this direction. This number is called the cutoff wavelength, and it tends to grow due to the compressibility. So we can understand that compressibility plays a destabilizing role in the inception of superficial waves. And following the way in which the cutoff moves as we modify the Reynolds number, we have the so-called marginal stability curve. Again, the darkest curve is the one related to the incompressible scenario. And in this case, we find that the threshold for the inception of instabilities is correctly recovered, the one due to Benjamin and Yi, which depends on the inclination of the plate. And as the Mach number is increased, this part of the curve tends to move towards lower Reynolds number, and this basically enlarges the unstable region of the curve. And interestingly, if we compute the ratio between the critical Reynolds number and the critical Reynolds number its incompressible limit, we find an expression that does not depend of the inclination of the plate. And we call this parameter Reynolds critical ratio. And in the next slide, we investigate the effect of the inclination angle on the stability of the film. So for instance, in this contour plot, we fix the Reynolds critical ratio above the critical threshold, and we vary the Mach number and the inclination of the plate. And of course, if beta is equal to 0, the plate is horizontal, so we cannot have a motion of the film. But as soon beta is higher than 0, the instability starts to manifest, and there is a quick saturation of instability because you see that around 10 or 12 degrees, the isolines tends to become vertical. And of course, the higher effect of compressibility is in presence of the highest value of Mach number we investigated. The final part of our study is devoted to explain these destabilizing mechanisms. And to do so, we follow the analysis of Whitham, who published in 1974 a book which is entitled Linear and Non-Linear Perturbations. And the idea is to recast the dispersion relation in order to recognize a first part which depends on the so-called speed of the kinematic waves. These waves are the response of the film to free surface deformation. And a second part, which is the quadratic part, that depends on the speed of dynamic waves. And we have two dynamic waves because when a wave starts propagating, we have a front and a rear of the perturbation that is originated by the response to momentum variations. And when we recast the dispersion relation in this way, we can recognize also in terms of mathematical formulation, we can recognize the hyperbolicity or non-hyperbolicity of the model. And in this case, this model is not perfectly hyperbolic because we have also higher order terms with respect to the second. We have third order terms that depends that are related to the effect of the surface tension. And so we have that this term here, omega, depends also on the Reynolds number and also on the wavelength of the perturbation. Anyway, the stability condition can be recasted in a way that we can say that the film is stable if the speed of the kinematic waves is in between the speed of the dynamic waves. And in particular, the only inequalities that has a binding character is the one with the CD plus, which is the velocity of the perturbation along the direction of the flow. And in this plot, we plot the speed of kinematic waves and the speed of dynamic waves with respect to the square of the wave number. And by this plot, we see that the speed of the kinematic waves is basically unaffected by compressibility, whereas the speed of the dynamic waves tend to go down as the Mach number is increased. And so the intersection between these curves tends to move towards higher values of the wave number. And this highlights the instability due to compressibility. And finally, to further elucidate the destabilizing mechanisms, we follow the analysis of Dice and Lavalle, because the instability is due to inertia. Basically, the propagation is due to the fact that the local flow rate cannot adapt instantaneously to variations of thickness. And so there is an imbalance between the wave crest and the wave flow. And due to this, we compute the inertialess value of discharge. Of course, we cannot take explicitly the limit as the Reynolds number tends to 0 because the compressible part diverges in this limit. But we can compute we can perturb around, again, a base state, this target value, and we can compare it with the full perturbation. So in this plot, you see expressed as a percentage the ratio between the compressible perturbation and the total perturbation, plotted against the Reynolds critical ratio we defined some slides ago. And you see that the effect of compressibility is enhanced at the lowest Reynolds compressibility ratio. So as soon as the critical threshold is achieved, and then this contribution tends to go to 0. And the reason for this is that the flow rate is increased by compressibility because you see that in the compressible formulation, you have an additional term, an additive contribution to the base state, which is instead due to gravity. So to sum up, in this study, we investigated the effect of a variable density in the structure of shallow water equations. And we see that this contribution is as additive terms, both in the continuity equation and in the conservation of momentum equation. And finally, we analyze the impact of compressibility in terms of development of superficial corrugations. And we see that the compressibility increases the instability of linear waves. And this is due to the fact that the compressibility contributes with an additive flow rate that enhances the destabilizing mechanism of inertia. So this is the end of my presentation. Thank you very much for your attention and also for this opportunity of presenting our research. And of course, if you have some questions or some curiosity, I will be happy to answer to you.